So that's me. I work at CU Boulder and NIST, and this isn't that's more of my day job. So let's get right into it. Thank you again for having me here. Okay. Oh, there we go. Perfect. So what is my motivation? It's consciousness is one of the most important and most exciting research problems to work on. But because I come from an AI background, I'm very interested in what are the implications of understanding consciousness and how we build AI systems. Unfortunately, I feel like talking about consciousness and AI is pretty taboo, especially from an engineering background. When I go to engineering conferences, I can't really talk about consciousness, even though I'm very interested in it, because people think that it's like too extreme. But I take a pretty conservative approach to how I deal with these issues. My question is, can I take existing physical law, things that we know and we have experimental verification for, and then can I tie the phenomenon of consciousness to existing physical law? So for me, the question usually revolves around, okay, here's the phenomenon that we agree that we call consciousness. Can I find a description of this phenomenon from existing physical law that then generalize across systems? And then the question is, okay, if I have another system that satisfies the same conditions that I used to describe consciousness in, say, humans or something, then I should be able to call this other system, artificial or otherwise, that satisfies the same conditions to also be conscious, if I wanted to be coherent. So, and once we have those the descriptions of consciousness that's like grounded in physical law, I'm curious, how can we take some popular philosophical questions and turn them into scientific questions? Where, there are particular ways in which we answer these philosophical questions traditionally. Can we answer them in a more empirical manner? And of course, there are implications related to meaning, ethics, law, etc. I'm no expert in those, but I'm always curious of what the implications are. Jumping right into it, there's a whole host of, it's a very familiar feeling what consciousness is, subjective experience, but it's also defined quite broadly. The discussions around qualia and phenomenal consciousness, access consciousness, etc. The most famous one is Nagel's description of what it's like to be that organism, for that organism. So I kind of have a working definition. I'm usually open to modifying those definitions when I see people give me suitable evidence to do so. So for me, the working definition right now is it's a process of generating information about the world by the system from the system's first-person point of view that feels like something. That seems like a broad enough definition that covers a lot of the things that people usually associate with consciousness. There's the issue of like feeling like something, there's the first-person point of view, and there's also this sense of like generating information about the world. There's a certain correlation with your external world that plays a role in what you experience. Let me know if I'm going too fast, please. So this comes down to saying something like, you are this human person in the physical world. You look at an external object, which is pretty much could be a black box of some sort. It sends signals to your head. There are all kinds of processes happening in your head that essentially produces something that we can call as the bubble of experience, where you view the flower from a first-person point of view, and it feels like something to view this flower. So this is a pretty simplified notion of what we mean by when we say of consciousness. So having said that, some of the most popular frameworks of consciousness, to be fair, there's also biopsychism, which is more like an identity theory, I think. But the two more popular ones are functionalism and causal structure theory. In functionalism, what really matters is how does a particular mental state, is defined by how it's connected to every other state. And the way, because I'm a computer engineer and I come from a computer engineering background, the easiest way for me to think about this is machine state functionalism, where you can essentially think about mental states as being defined by being in a state transition diagram, right? Every machine state is defined by what input it takes in and where does it transition to. And depending upon that, the entire state machine is defined by relations between a particular state and what its inputs and next states are. Of course, under functionalism, it doesn't really matter what the implementation is or how the implementation is achieved, as long as the system essentially follows the same functional structure. If the functional structure, the functional organization is realized, then the system is said to have global workspace theory and higher order theories, I think, fall under this category. And 1 second.
Right. Yeah, a little bit. Mic is a little bit didn't work. So.
What was the last thing you guys heard?
Just a few seconds left before. So.
Okay. Global workspace theory and higher order theory fall into this category. Another popular framework are causal structure theories. Causal structure theories kind of impose this importance of causal structure on top of the function. I think even though I think IIT doesn't focus on the function itself that much, the causal structure is all that matters. In that sense, where they say that it's not only, a pretty simple example with respect to IIT would be that it's not just that a particular function is realized, a particular function has to be realized in a very particular causal structure. The simplest would be a recurrent structure of sorts. So this theory, causal structure theory, is sometimes viewed by its proponents as like a step forward from functionalist theories. Causal structure theories, I would say that the human brain realizes consciousness in this recurrent manner. So this particular causal structure is of importance, and that is superimposed on top of the function itself. So obviously, IIT and recurrent process theory are kind of the theories that fall under this category. So based on those two frameworks, the question we can ask is, what are descriptions of consciousness? What do we really want from a description of consciousness, right? And one way to think about it is, in science in general, you want to produce a description of a physical system that has explanatory power of existing observations. You can look back and explain things you know, and also provide testable observations of things that you don't know yet, right? So in a manner that the providing testable predictions, and if it doesn't happen, then that falsifies your theory. Of course, there are other frameworks under which this is more of a Popper-based framework, but there are other frameworks where people don't really look for falsification itself. But this is one way to do this, do science in this manner. And if you're really looking for descriptions, then you can think of levels of descriptions. There's physics, chemistry, biology, computation. All of these are different kinds of descriptions of a system at different resolutions or levels. They all serve purposes depending on what you're trying to achieve. In that way, you can think of functionalism and causal structure theories as like descriptions of consciousness at like different levels. There's a very nice paper by Sarah Walker and Jake Hansen called Formalizing Theories of Consciousness, something like that. You can find it on Google Scholar, where they talk about this, where causal structure theories and functional theories are just descriptions of consciousness at different levels, right? And as I said before, CST is sometimes viewed as an improvement on functionalism. So my journey personally was, I started looking for what are the possible necessary conditions for consciousness. Two of the more popular criteria that's out there is Scott Aronson's criteria and Max Tegmark's criteria. Scott Aronson pointed out, the system has to show some kind of intelligent behavior. I don't think it has to go all the way to the level of Turing test, unless it's a human system or some system with language capabilities. But, it has to show some amount of intelligent behavior, unpredictability to outside observers. It can't be a giant lookup table or Boltzmann brain. This comes down to the structure itself. We know that, at least with respect to humans, you don't have lookup table human brains. You mainly have these recurrent structures that are produced in human brains, and full participation in the thermodynamic arrow of time. This, there's a very detailed explanation of what Scott Aronson means by this, but I usually think of this as like grounded in physical law to a certain extent. Similarly, Max Tegmark has a whole bunch of principles. A lot of them are pretty agreeable. I'm not going to go into them in detail. So based on those, we can kind of start asking the question, what would we like or expect in a scientific description of consciousness, right? The kind of things we would want is, in some sense, ultimately, we would want it to predict function and behavior exhibited by systems that we agree to be conscious. Human systems in general are intelligent, and you know, we are intelligent and conscious systems. So in certain extent, we should be able, I'm not saying all conscious systems are necessarily intelligent, but some of them are. So we should be able to predict certain amount of function and behavior. We should also be able to constrain physical structures that realize those functions. For example, we have to have an explanation of why we don't see feed-forward human brains. This doesn't necessarily mean that consciousness cannot be achieved by feed-forward systems, but it does. We do have to explain why there are no feed-forward human brains or some kind of animal brains. On the other hand, we could also think of a scenario where if in the world, half the humans are feed-forward brains and half the humans are recurrent brains, then you would have to come up with an explanation of consciousness in that universe where you would have to explain why they were both feed-forward and recurrent brains. So, and ideally, you would want it to be tied into existing physical law. I know there are theories of consciousness out there that ascribe new quantum mechanical interpretations or prescribe consciousness at the very fundamental level. That's one way to do it. But like I said, I'm very conservative in my approach. So I like taking existing law and trying to see how we can get aspects of consciousness or things that we prescribe to consciousness from existing physical law. And ideally, you would want to provide a third-person description, which is what science is about, on why a system would have a subjective first-person perspective. That, I think, is pretty important. So having said all that, the way I think about this, I don't have a better term for this, so I came up with it myself, called constrained functionalism. I'm sure there's a better term for this in philosophy that I just missed. But essentially, functionalism as it is says it's implementation independent. It says any system realizing the function would have the same mental state. That's the functionalism picture in mind. But this allows for attribution of mental states to a very broad range of systems. So constrained functionalism is where you say, okay, attribution of mental states to physical systems that realize a particular function, and the system itself is constrained by non-functional conditions. You put certain kind of like constraints on what kind of systems that achieve the function tend to have mental states. If you think about it, causal structure theories like IIT is a form of constrained functionalism. They essentially constrain it to recurrent systems or systems for which you can have a non-zero 5, right? And this is kind of tied to the fact that, you know, empirical evidence teaches us that all conscious systems that we know of have recurrent processing systems. So having said all that, you know, we have these functionalist pictures, we have these causal structure theories. The question is, why would we want a non-equilibrium thermodynamic picture, right? And the first one is non-equilibrium thermodynamics. One of the more powerful things about functionalism and computationalism is that it provides a description of systems that kind of like can be applied to a wide range of systems. There's nothing about the implementation itself that restricts the description. And in the same sense, thermodynamics is a description, especially non-equilibrium thermodynamics, which can be applied to all kinds of open systems, far from equilibrium, to any kind of system. There's nothing about the substrate of the implementation that tells you that you can, it's independent of a thermodynamic description, which is really nice. A great thing is concepts of information and entropy are already defined. A lot of new ideas in computation, in study of consciousness is heavily tied towards ideas of information and entropy, but these things are already defined in thermodynamics. They have a long history, and they're tied towards physical quantities such as free energy and dissipation. Perfect thing, it's tied towards physical law. The second law literally is the arrow of time. So you have something that's tied towards the thermodynamic arrow of time, which is great. And non-equilibrium thermodynamics can deal with open systems. Most of biological systems are open systems that are far away from equilibrium and constantly exchanging matter and energy with an environment. And while equilibrium thermodynamics usually deals with systems on or near equilibrium, non-equilibrium thermodynamics is powerful in the sense that it can deal with systems very far away from equilibrium. And finally, a useful thing about these thermodynamic pictures is you have this wealth of knowledge in both neuroscience and machine learning, which are both, starting to play a huge role in neuroscience for a very long time, but machine learning now, they're starting to play huge roles in how we study brains and study cognitive structures and how they relate back to consciousness. So a lot of these ideas in thermodynamics have connections to ideas in machine learning, like Helmholtz and Boltzmann machines. And then, of course, in neuroscience, you have the free energy principle, predictive processing, etc. So there's a lot of reasons on why we can look at a thermodynamic picture, because it has like a lot of positives going for it. I'll come back to the negatives in the end. So before we jump right into it, how are we doing for time? So that I can keep a track of it.
So, yeah, you still have like 40 minutes?
Okay, all right. Yeah, so that I kind of have like a time in my head. So a good thing to remember is another thing, maybe we can skip this slide, it's not that important. Let me jump right into it. So most of us are usually familiar with equilibrium thermodynamics. Equilibrium thermodynamics usually talks about, the most simplest way, the popular way of talking about is how the entropy of the closed system or an isolated system just goes up, reaches its maximum at equilibrium. Another way to talk about it is, can everyone see my pointer, my mouse pointer?
Let me see.
I
Maybe not in a YouTube. Yeah, we can see from YouTube. So yeah.
Okay, perfect. So obviously, one of the ways to talk about it is increasing entropy. Another way to talk about it is the free energy being minimized. There's also a way to talk about where you say the average work done in the system has to be greater than the free energy change. These are usually ways in which we describe this. The last one is actually just a restatement of this term here, that delta is greater than or equal to 0. These are ways in which you usually talk about equilibrium thermodynamics. And one of the problems is that there's an inequality sign everywhere, right? It seems like the conditions associated with equilibrium thermodynamics often is not highly specific. We ideally would want these to be like equality signs. We want to be dealing with conditions that are equality-based rather than inequalities. Of course, at equilibrium, we know that the distribution of the microstates is given by a Boltzmann distribution. And another important point here is, once the system reaches maximum entropy at equilibrium, there's no concept of time. The concept of time is dealt with increasing entropy, but once you hit max entropy, there is no concept of time with respect to the system. So equilibrium thermodynamics is great, but non-equilibrium fluctuation theorems are better, right? They deal with non-equilibrium open systems. There's been a rich history of work in this area, but over the last, especially I want to say 20, 25 years, this field has gone through like a silent revolution. It's amazing that all the very cool theoretical work that's going on there and slowly starting to trickle into other areas. A lot of people are now interested in taking these fluctuation theorems and applying them to biological systems to see what we can do. So there's like a lot of really cool work happening on there. But essentially, one of the most important turning points was this idea of Jasinski's fluctuation theorem. So the idea was, okay, essentially take a system that's at equilibrium state A, right? You drive it, you do some work on it, drive it away from equilibrium to a non-equilibrium state B, and then you let the system relax to equilibrium state EQ. And if you do this process a large number of times, this system will take different work parameters to go from this equilibrium state to this non-equilibrium state. There are a number of trajectories that the system can take, and each trajectory is prescribed by a work that needs to be done on the system to get it from A equilibrium to B. And Jasinski's fluctuation theorem essentially says is that the average of the work distribution, the average of the exponential of the work distribution is connected to the free energy change between these two states. So this is an equality statement, and you can see that if you simply use Jensen's inequality, you would go from this to this expression over here. That the average work is always greater than equal to the free energy change. But this is an equality expression, and it holds far from equilibrium, which is what makes it extremely powerful, right? There's another version where you can also think of the same, this in itself can be actually further decomposed. This comes from the fact that if you start off from an equilibrium state, you drive the system forward, you call that a forward process. You let the system come down to equilibrium, and then you drive the system backward in the exact same manner. The way to think about it in the exact same manner is imagine that there is a parameter lambda that you can change. And as you change lambda, work gets done on the system, and you go from an equilibrium state A to a non-equilibrium state B. When you go from B to B equilibrium, there's no work done in this relaxation process, so there is no work change here. And then starting from B equilibrium, you take the exact reverse path in how you change your lambdas, and you call that the reverse process. And there's a distribution, there's a probability of the work done in the forward process, and there's a probability associated with the work done in the reverse process. And those probabilities are always related in this manner. So that is a very powerful relationship. We can go even further to make it a little bit more simpler to think about it is, let's say that you have this microstate I, right? And over time, you are using some external work on the system. You're driving it from state I to state J to state K. You call that path from I to J to K as a trajectory. Let's call that trajectory gamma, and say that when the system went from I to J to K, essentially in that trajectory gamma over some time interval tau, delta Q, that's the amount of heat that was dissipated into a bath, right? So you can think of the exact opposite trajectory, the reverse trajectory, where the system was in state K. You can go back exactly the reverse trajectory where you go from K to J to T, and say that's the reverse trajectory gamma star. And the ratio or the probabilities of the forward to the reverse trajectories is always given by the exponential of delta Q, which is the heat dissipated in the forward trajectory over KT. And this holds arbitrarily far from equilibrium, which is very, very powerful. Which it says that, and you can, all the other higher order relationships about delta S being greater than 0 in a closed system or an isolated system, all those things come from the fact that the micro trajectories themselves follow this relationship. It is here that the fundamental arrow of time is built into. So these are for micro trajectories, right? These are for microstates. And we can't really work with microstates. What we really want to work with are macrostates. So in 2013, a little bit more, around 2013, Jeremy England came up with a version of the fluctuation theorem called the macrostate fluctuation theorem. He said, okay, let's imagine a system S that's in macrostate 1. Your macrostate is some macro observable that you can measure. And there is some probability distribution of the underlying microstates, call that PI, that all give you the same macrostate. And let's say you drive the system forward, you do some work on it over some time tau, and the system evolves from macrostate 1 to macrostate 2. And if you're in macrostate 2 at time tau, then there is an underlying probability distribution, PF, of the microstates that all give you the same macrostate, right? And you can also think about the exact reverse process, where you start from macrostate 2, drive the system in the exact opposite manner, reverse manner, and you end up with macrostate 1. And you can start from these initial microstate trajectories, do a bunch of integration steps, and show that you can come up with a macrostate fluctuation theorem which says if you're in state 2 and you drive it to state 1, the ratio was driving it from state 1 to 2 is connected by this huge exponential term, or this average over all microstates in here to here and over all trajectories from 1 to 2. Of course, this is really, really hard to do. I can immediately tell you, and this is one of the challenges of a non-equilibrium picture, is these kind of simulations are very, very hard to do because there's an extremely large number of trajectories, possibly infinite trajectories. But the point is that this is true for any system. If you have a system in macrostate 1 and you drive it to macrostate 2, then the probabilities of the forward and the reverse transitions are always related by this term here, which is the internal entropy change, which would be familiar, and this term is the dissipation into the bath. Beta delta Q is more, delta Q is the dissipation into the bath in the forward direction, but beta delta Q is more like entropy change. So this is kind of like a restatement of the second law for macrostate transition. It's telling you how the total entropy change of both the system and the bath should occur, right? So we have these fluctuation theorems now. Where do we go from here, right? So this is the work that I have done, but there's ongoing work in this where people are studying this idea of dissipative adaptation, where they say that, okay, let's say that you start off with the system in macrostate 1. Over time, it can either transition to this macrostate 2 or it can transition to macrostate 3. And then you can ask the question, what is the higher probability? After some time tau, that you're going to find the system in 2 as opposed to 3. And the idea is that if this forward process has a greater dissipation, is not only greater dissipation, greater work absorption and dissipation into the bath, then over time, this transition is going to look more likelier than this transition. So England, who proposed this idea, this hypothesis called the dissipation-driven adaptation, he essentially said that in time, if you keep driving it, even though some changes might look arbitrary, over time, some of these changes are going to be more and more likely, and those changes are going to look like having a memory of the work that drove them there, right? You can show that this delta Q is directly proportional to the driving forces between if you thought about RH as the driving history and S as the system, then you can show that all other factors being equal, those changes that lead to greater correlation between the end system and the driving forces will have a greater delta Q. And a greater delta Q also means a greater chance of ending up in that state. Of course, I mean, this might seem really small difference when you're taking into account only a few hours or a few minutes or something like that, but over billions of years, these things start to add up, right? So this is called dissipative-driven adaptation. So based on that, there are people working on this idea of thinking about your memory in such a way, where they say that if you really thought about memory is about correlations that you form with the environment that is driving you. And there's a lot of work trying to show that how, given the laws of, given non-equilibrium thermodynamics, certain processes are going to lead to greater memory over others. And the idea is, if we can view adaptation, and I can point towards sources for this if anyone have questions later, but if you can think of adaptation as learning the environment. Essentially, if this is more likelier, and that seems to be the end product of an adaptation process, then it would have a greater correlation with the environment. It seems like that system has learned the environment better. So if you can view that as adaptation as learning the environment, you can also view learning as adaptation in the brain, right? Where those changes that result in greater correlation are more with the environment are more likely over a period of time. And this correlation between the system state S and the environment history can be quantified using a mutual information term, right? I'm going to use that as my measure of memory. So that's one part. Here's the second one. So this is more of my work. All this stuff is ideas like Sean Carroll, John Carlos Baez, people in Jeremy England's groups have been working on. The idea that I'm more focused on is the idea of homeostasis. So homeostasis is the idea that a particular macroscopic variable essentially does not resist change to the environment and stays same. So if you really thought about that, that's essentially saying that you took a system in state 1, macrostate 1, you drove the system for some time period tau 1, and the system didn't change its value. So essentially the macrostate remains the same. And you can immediately see that the numerator and the denominator in this equation remains the same. So that essentially gives you an equation with 1 on this side you take negative logarithm on both sides. This side becomes 0. You get negative logarithm of a huge average term with an exponential in it. I won't go into the details of the mathematics, but if you use simple cumulant generation function, you can essentially write it as the sum of two terms on either side of it, because one side becomes 0. So you can write this whole thing as two terms, where one term is essentially the average entropy change. This is the dissipation part, but you can rewrite it as this. You can write as 1 over beta. So this is dissipation. This is also a form of dissipation. And this is the average dissipation change when you go from state 1 to 1. The other part is the fluctuations about that average. This whole term corresponds to fluctuations. So this is a very general definition of homeostasis in a non-equilibrium thermodynamic framework. It says that the average dissipation, or if you multiply both sides by beta, you can think of it as the average entropy change associated with this Macrostate change is equal to the fluctuations about that average. So if the average entropy change is large, then the fluctuations in the various trajectories that take you from 1 to 1 is also large. If the average entropy change or the average dissipation is low, then the fluctuations about that average is also low, and everything is concentrated in and around the mean. So having said all that, again, please let me know if I'm going too fast. There's a lot of material to build up to where I'm getting at. So having said all that, let me take a quick pause and say, so I've been talking about these I's and J's. These I's and J's are microstates, right? And these capital ones are macrostates. So we've been talking about how you have these microstates that all make up the same macrostate of the system. There's also an intermediate level that I'm going to start calling computational states, where I'm going to group a bunch of microstates together and call that my computational state. This is what we often do when you're talking about computation. We're not often dealing with microstates of the system. We usually group a bunch of microstates and say anything in the, the x-axis can be a particular, that's a degree of freedom, that's my computational state. So it's necessary to kind of differentiate between these different levels. The I's and J's are microstates. The capital ones and the capital twos, Roman numeral ones and twos are macrostates. And now we have these computational states in the middle. And these computational states in the middle is what we usually work with, right? So here's the major idea. When the system is homeostatic, we know that the average and the fluctuations about the average are equal to each other. So when they're both small, which means that the average entropy change is really small and the fluctuations about that are really small as well, that thermodynamic condition essentially implies that there is some grouping of the microstates of the system that make up this macrostate. There's a grouping of the microstates into computational states that will always satisfy this information bottleneck. What the information bottleneck is essentially a trade-off between the history, which is the memory, between this mutual information term is the memory, and this term here, this mutual information term is a measure of prediction. So if you thought about this system as a simple Markov system, it's a Markov system with certain computational states indicated by K, then this thermodynamic condition implies that there is some grouping of the microstates into computational states K that will satisfy this information bottleneck. Where RH is already correlated to the current state of the system, R1 hasn't influenced the system yet, but if the system is satisfying this thermodynamic condition at this point, then it's doing this computationally. Right? All it says is that the states encoded in the system are such that it allows a prediction of the next incoming input. And this lambda term here is a simple trade-off between prediction and memory. It kind of behaves like a pseudo temperature. We can talk about this later because I want to actually get to the more cool stuff about the consciousness part. So I'm kind of building up to it, sorry. Of course, if that seems a little off, you can even think about it as, since it's a Markov state machine, you can think about it as the transition probabilities from here to here. Essentially, you have a system here at time t, at the kth state, it's going to transition to the else state at time t+1, depending on some input here. And those depend upon two terms. All of this comes from the information bottleneck. And like I said, information bottleneck is in turn tied towards the thermodynamic conditions. And it has two terms. The first term here is simply, yeah.
So can you go one back?
Yeah.
That back. So, okay, so which one is the bottleneck variable? S.
Yes. The bottleneck, so it's essentially the idea that if you have only a fixed amount of memory, what information about the past should you store that will allow
I
you
know,
to...
I know.
Yeah.
I know the bottleneck, but I don't know which one. So the past is what?
H.
RH is the history, and R1 is the future.
Yeah.
Okay, and S is the bottleneck state. And so can you say the statement again? So you say that there are some, so R is the system state, or yeah, and there are some computational states that are exactly equal to the bottleneck variables?
Yeah, so the dynamics of the system, if you were to do if you were to study the system from a computational perspective, a system that satisfies this condition, this thermodynamic condition, would look as though it's performing the information bottleneck, that you can find some computational description of the system that behaves as though it's performing the information bottleneck.
So is the computational states coarse graining of the entire history or just of the current state?
Just of the current state.
So
the computational states themselves are some coarse graining of the current microstates of the system.
But then how can they be the whole information bottleneck? Because the information bottleneck would, I mean, the past future would need the whole, you would need to take, I mean, in general, you would need to take in the whole. Well, are you assuming it's a Markov chain?
I'm assuming it's a Markov chain.
Okay, I see. So the history is just the last state. The current state. Okay.
But the current state, but the inputs themselves, RH themselves, kind of affect which states have a higher probability of existing than other states. So if you thought about it, if you had an initial state and you drove the system forward, then based on what these inputs are, if the system is really satisfying an information bottleneck, then some states are going to be more likely than others.
What's an input?
I'm sorry?
What does this input mean?
You can think of the input as a string, like if you thought about it as a simple system, you can think of the inputs as being a string of symbols, ones and zeros.
So I is one, that's just one state of the possible R's, or?
Right, yeah.
Okay.
So you can think of R1 as having a probability distribution Pi1, where in brackets, right? Where I1 indicates a very particular string.
I1, next state. Okay, I see. Yeah.
Good?
Yeah. Yeah, I understand that. That's just the Markov transition matrix.
Yeah, essentially. I mean, this is more like this is the encoding probabilities, but yeah, this is the Markov transition matrix, right? It's what is the probability of going to the next state given the current state and the jth input of this one.
Okay, what's K?
K is the state of the system. K is the state of this system at time t.
Okay, I think this confused me. Like what you call system is now just some coarse graining, which happens to be the information bottleneck coarse graining somehow.
Well, no, I'm saying the system. Let's say so in thermodynamics, you just start off with a system that of interest. You draw a boundary somewhere, right? And you say this is my system. And if this is the system that satisfies the thermodynamic condition, then everything else about the computational states are a coarse graining of the microstates of S within S. The computational states do not make, so yes, you can think of S being made up of the computational states, but those come after. You start off with like a thermodynamic. So in thermodynamics, you start off by usually saying, what is your system of interest? You decide to draw a boundary and say, this is the system I'm interested in.
And that's S.
So, and that's S, yes.
Oh, what's R?
So R is everything else, the environment, essentially driving the system. You can think of it as R as some kind of external driving force.
But didn't you say, so you said that, okay, can you go, sorry, can you go one slide back?
Mm-hmm.
But I guess, I mean, like the thing is, if I don't understand this, I'm not going to understand anything.
Right.
So, okay, R is the environment, S is the system. So R is kind of the rest. So you have the system S, and then you have the rest of the universe, which is R. And those two things together are everything. And now
so I'm sorry, you can divide it further. You can think of a bath B connected to S, and then you can think of R. R is some input, like, because you can assume even the universe, you can divide it into a part of the universe, bath B, which you have no access to. You don't control what goes into the bath. You can't look into the bath. To be exactly specific, you can't look into the bath and have that give you extra information. You can think of it as R as some part of the universe that interacts with the system that you can actually think of it as an input to the system. So
R has the control parameter dynamics, kind of. Is it true?
Yes. Yeah. Yes.
Okay. So yeah, I can roughly get this. Okay. So there's some heat bath somewhere hidden, but that's,
yeah.
It annoys me, but it's fine. So now you say the information bottleneck of the past and the future is of R and not of S. So you take the bottleneck you construct, because you said S is the bottleneck variable for R, not for, okay. Is that so? So you kind of create the bottleneck of the control parameter dynamics. Yes.
I mean, if those R's are essentially, if you think of those inputs into the system as control parameters, then yeah, so S has a limited finite number of states, which I think is a reasonable assumption, that any S that you deal with will have a finite number of states. So it can't encode every past input it has seen. It only encodes some inputs about the past. And so S is the bottleneck variable of R.
Okay. I mean, yeah. Okay. It's kind of weird way around, but I guess I'm getting there now. I mean, at least I know what's going on roughly.
Okay.
Okay. So thank you. So maybe just keep going then. I'll ask again.
Okay. So if you thought about this as a transition, if you assume that this system is essentially doing this not just over one time step, but over multiple state transitions, then you can show that the state transition matrix will essentially have like a component that behaves as though it's maximizing predictions and another component that is essentially minimizing errors. This comes from the fact that if you have this thermodynamic description of a system in terms of energy and entropy flow, then there is some computational description that will satisfy, if you decided to talk about it as a Macrostate machine, then it'll behave as though it has these components of maximizing prediction and minimizing errors. So I think the main takeaway, to kind of like, without going too much in the weeds of it, I can talk about the math later if we want to have questions about it, is that there is a mapping between these thermodynamic, non-equilibrium thermodynamic descriptions and these computational descriptions, right? So having set all that up, so this is where I'm building on to. Oops, I think like I'm sorry, let me re-share my screen.
Yeah, please.
Does that work?
Let me check in YouTube.
Yeah. Okay, here we go.
Yeah.
Okay, so
between. Oh yeah, sure. Okay.
Okay, good. So having built into all that, this is the main crux of it. We're back to the consciousness part. So I'm saying that the main hypothesis here is that a system S is conscious if it satisfies these two non-equilibrium conditions concurrently. Condition one, call it TCC1, whatever. Condition one is that the system should show this dissipation-driven adaptation, which essentially is how the system essentially builds a set of correlations with the environment and essentially forms the memory part of it. And the second is that it should show this homeostatic condition, where it uses this first condition to build the memory, and it exploits the memory to do prediction in the second condition. So if a system satisfies these two, I'm going to say my hypothesis is that the system is conscious. So let me quickly run into that. The first part is the first condition is not that new actually, right? Because if you study complexity, then a lot of times people use this mutual information term that I use as memory as a measure of complexity. So if I were to just say the first condition alone, then that's very similar to a lot of other existing ideas out there that says more complexity, more consciousness. That isn't enough, because that essentially attributes consciousness to a wide range of things, right? Because you can think of, if you took a burning piece of wood, then the burning piece of wood has some memory of the fire that burnt it. The burnt piece of wood has some memory of the fire that burnt it. That essentially doesn't really mean anything. So the first condition is pretty broadly used already. I think what adds greater strength to this framework is the second condition, which essentially is the idea of the information bottleneck. So let's actually go and explore the second condition a little bit more in detail, right? Because the first condition as it is, it actually doesn't exclude a lookup table from being conscious. Because technically a lookup table that continuously updates its memory with the latest input, where it like chugs out the, last in, first out kind of thing. That essentially would be a system that satisfies TCC1. So that isn't enough. So exploring TCC2, one of the things that it does immediately that we can tell is that because satisfying that homeostatic condition at lower dissipation implies an information bottleneck, it essentially implies that the system will show some kind of predictive behavior, where it's exploiting the memory it has to predict what's coming next. That prediction is often considered as like one of the central hallmarks of intelligence. So in that sense, it'll do that, where it accounts for a certain amount of intelligent behavior. The next question is, okay, the good thing about these conditions is that they are not implementation or substrate independent, which means that they will generalize, right? Because exactly like functionalism, thermodynamic conditions can be applied on all systems, but the other way is not true. Not all systems satisfy the same thermodynamic condition. You could have a system that essentially implements the information bottleneck computation, but need not satisfy the underlying thermodynamic condition. So it's not like a two-way relationship. And one way to think about the second thermodynamic condition, the homeostatic condition, is that it's very close to an energy efficiency criterion. So it's highly likely that a lot of our modern machine learning systems, if we're mostly familiar that these systems take a lot of energy and they have serious issues around power dissipation. And this idea says that it's highly likely that most of these computer simulations of the brain will not satisfy TCC2, even though they might implement the same algorithm. So I think in a lot of sense, like some of existing theories like IIT, which says that current von Neumann systems will not be satisfy, would not be conscious. This will make the same prediction. We would of course have to test it and actually do the testable prediction, but this will say the same thing in the sense that current modern machine learning systems that need these giant servers will probably not satisfy this energy efficiency criterion that is inbuilt within the TCC2 and hence will not be conscious. What about which kind of structures does the thermodynamic framework say is associated with consciousness? IIT, RPT usually associated with the recurrent structures. What about the thermodynamic framework? Scott Hansen calls this the pretty hard problem. And the answer, to be honest, is it depends. So the thermodynamic framework doesn't necessarily rule out both feed-forward or recurrent structures, right? What it says is that the question always is put forward in this manner. If we bought a recurrent structure and a feed-forward neural network that has the same function, that does the same intelligent behavior, which one of these two is conscious? Some theories will say, functionalism will say both are conscious. IIT, recurrent processing theory, will just say just the recurrent structures are conscious. On the other hand, a thermodynamic framework will say, well, hold on a second. Both can be conscious or neither can be conscious. The only thing we can do is actually say, okay, this is my system of interest. Let me ask the question, does it actually satisfy both these conditions or not? Because the question isn't really, is consciousness associated with just feed-forward or recurrent structures? The question is more, why do all the conscious systems that we know of biologically, or that we agree to be conscious, are all recurrent in nature, right? Because I can definitely say, maybe it is the case that with carbon-based and organic structures, those substrates can only satisfy these conditions under recurrent structures. They can only satisfy the necessary thermodynamic conditions of consciousness by using recurrent structures, which is why we probably don't have feed-forward brains, right? But on the other hand, you could have superconducting neuromorphic computing circuits, feed-forward circuits that satisfy the necessary thermodynamic conditions, in which case you might have to say, oh yeah, those superconducting feed-forward neuromorphic systems are conscious. Now, you might say, oh, that seems silly. No, it's not, because all we can really say is there is a reason why we don't find superconducting neuromorphic circuits around us. Because these systems usually operate at near zero temperatures, right? So we can only ever, so it kind of shifts that question, that philosophical question, to like more of a question saying, okay, under the conditions that we see, under the environmental conditions that we see, we can best explain why these systems occur in recurrent systems. But it might very well be the case at that like near zero, absolute zero temperatures, maybe feed-forward systems with all these new kind of superconducting materials could be conscious. How are we to rule that out, right? At best we can do is ask the question if those systems satisfy the same conditions that we associate with consciousness in humans. Moving forward even further, I think we have to kind of get out of this mentality of thinking about consciousness as associated with particular states at fixed points in time. It's better off thought of as a dynamical process that changes in space and time. And then with that comes the idea that consciousness need not be an all or nothing framework. It's gradual and it will depend upon a pseudo temperature parameter like lambda. I can come back to lambda later if we have time. And we can always ask the question, given what is the likelihood that over time, structures that satisfy this condition number 2 emerges at different scales? If this condition really is the best description of consciousness in physical systems, then how likely is it that structures that satisfy this condition over certain spatial and temporal scales arise? And that would essentially give us like, why do certain structures arise with consciousness? Are conscious systems inevitable given the laws of thermodynamics? Mapping back to the information bottleneck allows us to connect this to existing work in free energy principle, predictive processing. I know that you guys had an information generation hypothesis, self-organized criticality. There are ways to connect existing work onto this. I haven't done it. I'm hoping I can get more people interested to do it because I'm not expert in many of these ideas, but I'm hoping that the connection is there to see. So all I've talked about until now is essentially these easy problems, right? What people think of them as the easy problem. But what I really need to be talking about, and this thing is the thing that people really expect, is the hard problem. I'm using hard problem in quotes. The hard problem is really the problem of phenomenal experience. And everything that I seem to be talking about now, this seems to be information processing and doesn't seem to get to us to phenomenology. And this is where I say that the thermodynamic framework takes what's called an illusionist position. The illusionist position is really that we think that we are realist about consciousness. We think that, yes, you do have consciousness. you do have subjective experiences, but we do not agree to the framing of the hard problem. The hard problem frames it in a way of qualia or phenomenal properties that simply makes it, by the very way the problem is stated, makes it impossible to actually solve the problem. We're instead saying that you don't have phenomenal properties. I point to the statement by Keith Frankish, who's one of the leading figures in illusionist ideas of consciousness. And we say that these properties are not really phenomenal. They're what we call quasi-phenomenal properties, where they're actually like every other physical property, but they just appear to be non-physical. And if you can come up with a good explanation of why some of these properties would appear to be non-physical, or why some of these things appear to be non-physical, then that's it. Essentially, if you can solve the meta problem of consciousness, that's it. You don't have to solve the hard problem. Solving the meta problem essentially ends the whole thing. So these quasi-phenomenal properties, essentially, they usually, Frankish has attributed the idea that resource constraints might be one of the reasons why, because we don't have an infinite number of computational resources, we cannot essentially process all signals at the same resolution. We have to process different signals at different resolutions. And because of that, some of these signals get misinterpreted as phenomenal or having this subjective feel. I want to immediately say that just to reinstate, we're not saying that consciousness is not real. I am saying that consciousness is real. You do feel pain. All I'm disagreeing with is that pain is made of qualia, this phenomenal property that we just made up. So how do we propose to essentially explain how quasi-phenomenal properties arise? We're essentially saying the same thing that Frankish is saying, that the lack of sufficient resources in the brain is the reason for these quasi-phenomenal properties, why these properties get mistaken to be phenomenal. We're saying that both TCC1, which is a memory constraint, and TCC2, which is essentially a resource energy efficiency constraint, essentially causes the brain to compress signals. That's what the information bottleneck is. It's a compression. It's a coarse graining of these signals to different levels. Some signals are coarse grained to a certain amount, and other signals are coarse grained to a larger amount. And those signals which are so heavily coarse grained become so coarse grained that we start thinking of them as phenomenal. A good way to think about it is if you thought about all problems or how all things that happen with respect to cognition as being easy and hard, Chalmers creates a very strict division between those which are easy and those which are hard. We're saying, no, they're all kind of physical. It's just that those which are considered easy are coarse-grained to a certain amount, but those which are considered hard are increasingly more and more coarse-grained, to the point where they stop being physical. This whole notion of mental and qualia only arise because these signals are so heavily coarse-grained, and these are interoceptive signals. My guess is that these are interoceptive signals that's arising from outside of the system S that is conscious, that's doing the work of a conscious system. And all these interoceptive signals, there's an argument to be made on why they are more coarse-grained than exsensory signals, but they're coarse-grained to such a heavy point that they start feeling non-physical. And that essentially gives rise to these phenomenal or subjective feel, right? So right now, all I've done is I've explained that why you should have a certain predictive quality, like an information generation process, where you're constantly taking in signals from the outside and you're predicting what's coming next. I've attributed the feeling of the quasi-phenomenal properties that we experience, that we usually mistakenly call qualia, to interoceptive signals that are heavily coarse-grained. But the one thing that I still haven't done is explained why we have a first-person point of view. Why should any of these feel like they come from your point of view, right? I still haven't explained that yet. So I want us to go back to the information bottleneck again. This says that if you really looked at it, it says that this system S essentially takes in these inputs and then makes prediction about the future inputs, right? All the system generates predictions about are signals outside of it. The system, let's not call it a system, let's call it the process. That's a better way to think about it. Consciousness isn't about a system, it's about a process. This process is about generating predictions of all inputs to the system. If S0 is your conscious system, and the process of consciousness is essentially predicting inputs to the system. The one thing the system cannot do is make predictions about itself. It cannot make predictions about S0 itself. It cannot make predictions about a subsystem of S0. It can only make predictions about signals coming from outside of it. Because it cannot make that prediction of subsystems of within the system, within S or S0, we're saying that essentially is what the hypothesis is. That's what leads to this idea of a first-person view. You can only have a model of everything else outside of the conscious process itself, but you cannot have a model of the process that's generating the consciousness, which is why it seems very weird where we have this model of a first-person point of view, but not of the process that generates it. This is sometimes referred to as phenomenal transparency, where you have the contents of the process. The process is essentially generating content of incoming inputs, making predictions of those, but it cannot make predictions about the vehicle, the neural systems that's generating the process itself. And that is because of the information bottleneck. And that results in the first-person point of view. A very loose analogy to think about this is, think about Alice and Bob in a room, right? Alice is sitting in a chair and Bob is reading. And you tell Alice to describe everything that's happening in the room. Alice writes, Alice is sitting in a chair writing, and what everyone is doing, and Bob is reading. And then you tell Alice to remove any mention of what she is doing. And this time we get the same description, Bob is reading. You can see how when you remove the process, which is Alice here, that is generating the descriptions of what's going on, the description of what comes out seems to come from a certain different perspective. And that's what we're saying is happening here. Because the system cannot describe itself, or cannot describe the process generating those descriptions, it results in this first-person point of view. So I'm almost done, I promise.
Okay. So yeah, just almost 1 hour. So yeah, please.
Yeah, I'm right near the end.
Okay.
So what do we have here, right? So I started off with this working definition of consciousness that says consciousness is a process of gaining information about the world by the system from the system's first-person point of view that feels like something. So, and then I prescribe two conditions that I am saying essentially does the following, right? It accounts for generating predictions about future inputs and using those inputs to correct errors. So that essentially is the process of is generating information about the world. It compresses and coarse-grains those inputs to varying degrees, which results in this quasi-phenomenal subjective feel to them. And finally, because the system or the process cannot model itself, it ends up creating this transparency or this first-person point of view. So I feel like these two conditions, it's still very early days. There's a lot of work to be done, but kind of can allow for us to account for a lot of these different things that we associated with consciousness. And the good thing is it's tied to existing physical law. Everything about the fluctuation theorems is established physical law. We don't need new interpretations in physics or new psychophysical laws to get us there, which to me is a bonus. Of course, there are some immediate questions to be asked that everyone will keep wondering about. What happens if you are S, you are the system S, and you have a consciousness? What happens if there's another subsystem within you that is also satisfy the conditions? Is it also conscious? There are three possible ways to get out of this. One is to propose an exclusion principle and say the biggest system is the only thing that's conscious. This is what IIT does in a manner. I will avoid it because it doesn't come from physical law directly. There's nothing starting from fluctuation theorems that tell me only the biggest system has to be conscious. Second is to say this situation will never occur. I have heard some proponents of IIT say something similar. I don't see why not. There's no reason to think that there's only one system that will have. There's only one system that will satisfy at one scale that will satisfy these conditions. You should expect multiple systems to satisfy. The easier way is to say, actually, they both can be conscious. You could essentially think of yourself as the subsystem. You assume that you attach a microchip to yourself, and you and the microchip together is the joint system. and let's say both S and S0 both satisfy these conditions of consciousness at the same time, and I'm saying that is fine. Remember, when S satisfies the conditions of consciousness overall, S0 and the microchip are subsystems of itself, and S cannot be aware of them. S will never have a conscious experience of them. S will at most have conscious experience only of the inputs to S. So it's completely fine for conscious system S to exist at the same time as the conscious system S0 to exist. You will continue to interact with this microchip so these two systems have to be very tightly integrated for this system to actually be conscious, the joint system to be conscious. So you will essentially continue to interact as a conscious system by yourself, interacting with this microchip, and you're getting inputs. While the joint system overall will continue to interact as one single conscious system, unaware of the processes that generate the consciousness in the first place. So this is very similar to the non-trivial information closure idea, that you can have these multiple conscious systems at different levels as long as they cannot have information transfer between themselves. It's the same picture here. I'll skip these over here, and I'll get to pretty much near the end. Some of the challenges that lie ahead of us, I think that I talked about how there must exist some grouping of microstates that produce the computational states, but we don't know how exactly to find those computational states. Because right now, neurons and synapses are very much in vogue, and we all want to use them to build ideas about the brain, but there's no reason to think that glial cells, astrocytes, neurotransmitters, all those other proteins also play a computational role. So we don't know how to group these microstates into computational states, and that's a problem. Anyone in non-equilibrium thermodynamics will tell you simulating state trajectories and calculating these work dissipation distributions is very, very hard. It's incredibly hard for any system of even like remotely small sizes. So that's a problem there. But on this end, there are very clever people working on some very cool algorithms to make this simulation a little bit more tractable. There's still the giant issue of how some of these state trajectories lead to a very particular experience. I don't know the answer for that yet. I'm still working on that aspect of it, on whether or not, how important is the substrate itself to a very specific experience. I am not completely sure on that yet. Another point to note is that there's a lot of work needs to be done to take these thermodynamic descriptions, because it operates at a very different level, and connect them back to neuroscience. There's a lot of work that happens in like bench neuroscience, and we need to be connected to. Thermodynamic descriptions do not replace the neuroscience work. Neuroscience work is where the focus has to be in systems that we know are conscious. Thermodynamic descriptions, in my personal view, essentially ties all of these ideas back to physical law and says there doesn't have to be anything mysterious about all of this. We don't need any new physics. All of these things can possibly be explained under existing law. Finally, I'll quickly point towards why I think these kind of ideas can lead to exciting work at the intersection of consciousness and AI, because right now, if you thought about dividing it into a consciousness, intelligence, and energy efficiency, you have this giant CPU there that's running a state-of-the-art machine learning algorithm. It's highly intelligent. It's not super energy efficient, and we don't expect it to be conscious. But you have the human brain, which is also highly intelligent. It's energy efficient and is conscious. So it seems like these thermodynamic conditions are essentially prescribing an energy efficiency condition. So the question is, as we build more and more energy efficient hardware, it might be the case that we might be building these chips with new material, new architectures like neuromorphic systems are, that's going to look more and more bio-inspired, right? And as they start looking more and more bio-inspired, if they stop looking less like these chips or these systems and start looking more and more like neurons and synapses based on artificial material, then, that satisfy all these, they're intelligent, or they allow for intelligent behavior, they're energy efficient, then we might have to, be open to the possibility that these systems are conscious too. And I'll point towards that and say that I have another paper on arXiv called Rethinking Neuromorphic Design. It's under that title, which essentially says that there's this very exciting work by a group down in UCLA. And I think there are other groups. I think there's one in Japan in the, I want to say there's a Nanomaterials Institute there. And they do work with the silver nanowires. Essentially, these silver nanowires have membrisive properties, in their junctions. Essentially, memristas are hardware that behaves like a single hardware unit that behaves like a synapse. So they essentially grow these hardware chips. Essentially, this middle part here of a chip is a network of nanowires that's grown in a very specific density in a small world network architecture. And clearly, you can see that this is not designed. You have a bottom-up chemical process that produces this chip, and they've used these chips with no software in the middle over there to do very simple time series prediction tasks. So I'm currently working with these groups to figure out if these kind of systems actually satisfy these thermodynamic conditions. If they do, and so they're energy efficient, they can be used to do some very simple intelligent tasks, and they are, then we might, and given the architecture, the structure of these systems, we might be open to the possibility that these systems could be artificially conscious. So that's one of the things that I'm currently working on. So, like I said, a lot of these are essentially, you can think of them like me just pondering about these ideas. I'm hoping that I can, generate more interest and get more people excited, because I think there's very cool work to be done, not necessarily even to the consciousness part, but even at the intersection of thermodynamics and intelligence. And I think there's a lot of cool work to be done to figure out how to do simulations. And especially if you're a hardware engineer and you're trying to work with these new materials, then there's a very cool, exciting work at the intersection of AI and consciousness for hardware engineers. So yeah, I'm done. Thank you very much.
Okay. Yeah, thank you very much for the talk. Yeah, it's kind of interesting for me, like seeing from more like non-equilibrium thermodynamic perspective. So we have several questions in a Slido, so I will read some questions. So I will share them.
Okay. Yeah. I can stop sharing mine.
Yeah. Okay, please.
1 second.
Right.
Stop share. There we go.
This one, I think. Yeah. Can you see the Slido? Yeah. Okay. So maybe in a YouTube, it's not open yet, but let's see. Yeah. Okay. So now it's working. So let's ask you a question. So is somebody in posting this question? Maybe not. Okay. I'll read one by one, and then get back to the. Okay, so can we quantify the level of consciousness based on TCC1 and TCC2? How can we test the validity of the TCC1 and 2 as the conditions of consciousness?
So there are a couple of ways. So in terms of whether they quantify a certain amount of consciousness, I don't, how do I put it? I don't know quantifying the level of consciousness can be achieved by a single parameter, but one way to possibly think about it is if I can quickly share my screen again.
Okay.
1 second. No, here it is. If I go back. I'm not particularly, so this way to quantify the level of consciousness gets tricky, because I think it comes from IIT, because IIT uses a single measure, and now I think they use more of a structure, information structure of some sort to calculate the level of consciousness. I'm not particularly a fan of a single value itself. But if I were to, if someone asked me to pick a single parameter, one could think of this lambda parameter as it is, because the lambda essentially acts like a temperature parameter. If lambda goes to really small or really high, it's highly likely that the way the contents get disrupted in the way information processing occurs might be closer to like sleep or epilepsy or something like that. If you were to think of epilepsy and death are both highly ordered, and if you went to like sleep in the other end, well, then if you had like a random firings in the brain, then those come due to the way the lambda values are manipulated. So the lambda values might be a way to do it, but I don't necessarily think of it as a level of consciousness, because it's, it's hard to say what the level of consciousness means when you're already conscious. It's easy to say, distinguish between consciousness and unconscious, right? That's pretty straightforward to say, if you're anesthetized, then you're unconscious. If you're not, then you're awake and you're seeing all these things, then you're conscious. But once you're within the stream of consciousness, I don't necessarily know what it means to say someone has a higher level of consciousness than the other person. I don't know what that means with respect to content, with respect to awareness. That gets a little bit more tricky. But if push came to shove, someone had a gun to my head or something, I might say lambda might be the way to do it. Another way to possibly, like I said, all of these ideas are evolving. So another way to possibly do it is to ask the question, if you were to think about a particular spatial region where you draw the boundary and say, that is my S for which I'm calculating whether the system is conscious or not, you can ask if that S shrinks or that S becomes bigger. That might be a way to think about level of consciousness, but I'm not committed to that. I haven't really thought about it. And the other question was, how do you falsify such a picture? I think one way to do it, and this is where I think it might help with respect to neuroscience, is to take a system that we agree to be conscious, and then, or if we can identify, say, the neural correlates of consciousness, where we can strictly say that this part of the brain is strictly associated with consciousness from our experiments, and these parts are not. And then ask the question, does this part of the brain, when you are conscious, satisfy these kind of conditions? Can we make not necessarily the direct trajectory calculations, that might be too hard, but can we find measures that are proxies for calculations of entropy, energy dissipation, so on, that allows us to make rough calculations about whether they satisfy these conditions? Then that might be one way to do it. There's very interesting work by Daniel Bassett and Chris Lin, who recently used, I think, work from fMRI images to try and find a proxy for entropy calculations in the brain. And they were able to show that the brain operates in a non-equilibrium steady state away while it's normally operating, and they were able to find proxy measures to indicate that when entropy goes up and when entropy comes down. So those might be ways where, if we identify, so this is where, I think this is the problem when you deal with such a high resolution of thermodynamics, is that you kind of lose this connection with the neuroscience a little bit, right? Because, for example, right now, Global Workspace and IIT have like this adversarial collaboration where they're trying to identify which part of the brain is associated with consciousness, the frontal versus the rear part of the brain, right? And that is useful to do when you're operating at a certain level of description. Right now, as it stands, the thermodynamic description is such a high level, I don't know how to map it back to specific parts of the brain yet. Again, I don't have enough time in the day to actually focus a lot of my time and effort into this, but I think it'll be very useful to try and understand where the connection exists. But one way to falsify would be that. Another way to falsify it would be, let's say we take known organic structure, organic material that makes up our brain, right? There's a bunch of organic material that makes up our brain, made up of carbon, hydrogen, oxygen, nitrogen, and ask the question, with material very similar to our brain, can we construct a structure that satisfies these conditions and exhibits the level of intelligence that we do? Because if we can, then there's a question on why those structures didn't evolve over time thermodynamically. And it might be the case that I personally would see it, I would find the thermodynamic description very hard to believe if we can construct feed-forward brains that are as intelligent as we are and satisfy the same conditions and as energy efficient. I would see that as a good way to say, this description doesn't capture everything. So some might argue that that would be one way to possibly do it, but I'm still not, there might be other ways to do it too. Yeah.
Okay, so maybe next questions. Okay. Yeah, it's kind of it's related, but so from the anonymous person, would it be fair to say that the very high level of coarse graining is required in order to have a stable experience of the world? Does it make sense?
Yeah, I'm not quite sure what a stable experience means, but I think any coarse graining at the level at which I guess I'm not quite sure, because there's coarse graining at multiple levels. There's coarse graining from microstates to macrostates, and there's coarse graining from microstates to computational states. So I'm not entirely sure which coarse graining they're talking about. So if that was available, maybe we might be able to like discuss it. But I'm not quite sure what level of coarse graining that they're talking about.
Okay, so maybe there's some ones in it, or maybe not. Maybe not. So yeah, maybe we can go to next questions from the Christoph. What is this W and O?
Without.
Let me see. I don't know. So can you see that?
Yeah. The WO is without.
Okay.
I think it goes from bottom to up.
Right.
Maybe I don't. Oh no, this is 1108. Okay, as in without the very high level of consciousness, we would still work with physical system, not information. What we experience is just a model of reality, not reality itself. No, I agree with that. Like the experience is essentially the predictions that you're generating, the consciousness. So even the way that question is framed, right, that there is this experience and then there is us to experience it. There is this experience that we have, and then there is this us that is experiencing it. Even talking about it that way, comes down, puts us in this homunculus pathway. What all we have is a process that generates both this first person point of view and the reality that this first person that's seen from a first person point of view. So I agree that we don't actually see reality. All we have are models and predictions that we make of the external world. And hopefully, if our brains are satisfying, good, if our brains are really satisfying these energy efficient conditions, then we want a good model of reality. If you're constantly making errors about what's in front of us, then you're going to think you're going to be walking down a blank road when there's really a car heading towards you, and that kills you off. So yes, you're having models, but you're having good models.
Okay, yeah. So maybe next, would you say that based on your theory of society made of conscious individual is conscious by itself?
So this goes back to the idea that so I think I think Eric Schwitzgebel came up with this idea because this was one of the points against IIT in its original, in one of its earlier forms, where if you put a large number of everybody in China together or everybody in the world together and have them really well connected, each of them are individually conscious, but is the whole thing conscious overall? Let's say that we manage to connect all these physical systems of individual consciousness together to form a larger consciousness as well, where all the people together are consciousness. This is the idea that I was talking about before. I'm going to quickly share my slide again. There we go. Oh, here it is. So instead of the microchip, if you think there's 10 other people, all of them conscious by themselves, you can all be really well connected, integrated, and somehow in some manner where the joint, all 11 of you together is also conscious, right? Then yes, that whole system, if all of the entire system behaves as a conscious, satisfies those conditions, and they behave as like one entity reacting to inputs in a very specific manner, then we have to be open to the idea that the whole system is also conscious. But remember that the whole system being conscious does not remove the fact that the individual systems are also conscious. You can have both of them to be conscious at the same level, because the Uber system, let's call it an Uber mind of some sort, because these systems are now subsystems of itself, generating the conscious process of the bigger system, the larger system will only see these inputs from its point of view. It cannot so just as you cannot have a conscious experience of the process that generates your conscious experience, the same applies to the Uber mind as well. So the internal systems can themselves be conscious as well, constantly reacting to these different inputs that some of them see and others do not, while the Uber mind together can also behave as one single conscious entity.
Okay, yeah, right. So next questions. Okay. How do you account for performance of mental state, concept, ideas, and consciousness in a statistical framework?
I think like that actually is a very interesting question because let me stop sharing this.
Oh yeah, sorry. Maybe I should share.
Oh yeah, you should share. Yeah.
Yeah.
So if the permanence of mental states. So I think this comes down to by mental states. I'm assuming ideas and concepts. There are ways in which I didn't talk about it in here, but there are ways in which certain states with probability, with higher probability, will take over. So it might be the case that this is a constant process because this is a constant feedback process, right? You are generating predictions and you're constantly taking in inputs from the outside, including inputs from within your brain. So it could be the case that there is some kind of top-down and bottom-up process that allows you to maintain a particular thought in a certain amount of time. And this, I think, is still an open question on how the statistical framework maps onto the actual system, because you're not experiencing a distribution of ideas. You're usually experiencing like a single idea or a single experience. You don't have a distribution of experience at any time that you actually experience. So, couple of I can throw out a few conjectures in the sense that there might be something akin to an attention mechanism. I think of an attention mechanism more like a machine learning sense, where certain states have a greater amount of priority over others. It might also, or certain values in a distribution, a certain states in the distribution have a greater priority, and that's the one you experience. But there might be others too. And I am not entirely sure what is the exact answer yet. Okay.
Okay. Yeah. Thank you. So we have only two more questions.
Yeah.
Okay. Okay. So if we make a more energy efficient hardware than the human brain, will the hardware process higher level of consciousness than human?
I think this once again goes back to the idea of whether we want to talk about levels of consciousness. So it doesn't necessarily have to be more energy efficient. It also comes down to how much memory it has, right? There are two conditions. Because if the system can only hold 10 bits of information, then, it doesn't matter if it's more energy efficient than us, it can only hold 10 bits of information. That's not useful enough to be more conscious than us. So this is why talking about consciousness, levels of consciousness as like a single scalar is not that good. You have to have, it's more of a vector where if you had something that had the same, say, the memory complexity of the brain or something, and then it was also more energy efficient, I still don't know what a greater level of consciousness would mean. Maybe if it had, let's say, I could think of a scenario where if you had a hardware that had greater memory capacity than the human brain does and is more energy efficient, then it could be that it has a different experience. I don't want to call it same level. It might be the case that we were talking about how some signals in the human brain all signals are coarse-grained, but some are more coarse-grained than others, right? And depending upon the level of coarse-grainedness, some of them have these phenomenal feel to it. So I think, so I'm saying it might be the case that hardware with the same amount of complexity and is more energy efficient might not have to coarse-grain that signal as much as we do, right? So something that feels like pain to us because we have coarse-grained it might not feel like pain, might be a little bit more clearer, so pain is more subjective as opposed to say shape or color or something that's a little bit more clearer. And it might be less like pain and more like color. So again, this goes back to this idea of like thinking about it in terms of levels is a bad way to think about it. It's more that it might be a different kind of conscious experience that the system might have.
Yeah, right. Yeah, okay. So the last question from Slido. So are you familiar with Lane neuromorphics and their work on fully analog neural networks? What do you think about their approach?
I'll say that let me put it this way. I'm very familiar with their work. I think it's interesting. I have a whole range of objections to how they're doing it, but that's my own personal thing. I think I'm pretty sure Christoph, and I know Christoph from Twitter. I think I've seen some of his. So if you want to DM me, you can feel free to DM me, and we can talk about this in private. But yes, so let me put it this way. I give them a lot of credit because they are very different from how current AI hardware systems are being done. But I still don't think they go all the way. Let me stop it at that. Did we lose? Oh, can I take the question from the chat?
Yeah, do it.
Yeah, sure.
Because it's my question.
Yeah. Hi, Martin. So yes, so again, this goes back to, I think, so essentially you're saying if I build are you talking about a physical epsilon machine?
No, I mean, no, I actually don't. But I mean, if you want, you can. But I'm thinking, okay, so I just take some Markov chain, which I can just run on my computer. I built its epsilon machine, which is then the epsilon machine of this Markov chain. So it's kind of the informational, like the optimal informational body.
Right.
And then is it conscious because it has this environment and it basically has everything. Maybe it doesn't have a heat bath or thermodynamics, but yeah, I don't understand this thermodynamic stuff. So that's why I'm asking, I guess.
So I think this goes back to this idea of, so the epsilon machine is essentially like a computational functional description of a system, right? So we're asking the question, I think you can correct me if I'm wrong, but I think that the underlying question here is, if an epsilon machine might do the same functional thing that the thermodynamic system would do. And why is it conscious? If it's not, why isn't it conscious? And this comes down to this idea of, like, everything I seem to be saying, why can't a functional system that just implements that function but does not satisfy the thermodynamic condition, why can it not be conscious? That essentially comes down, I think that's the fundamental question there. I might be wrong.
No, maybe the question is, why doesn't it satisfy the thermodynamic condition? Because I understand this argument that if it doesn't satisfy the thermodynamic condition, then it's not it. But it seems to at least satisfy the second condition, maybe, but maybe not. I don't. Yeah.
I mean, you can think of a system. You can think of an epsilon machine with a memory that's changing, constantly updating. That's also doing the information bottleneck. So the question comes down to, yes, I think you can. So it comes down to the physical way in which you build the system, right? So you can build an epsilon machine with a certain kind of material that might satisfy these conditions. And I guess, like, you can think of these conditions as more descriptive rather than prescriptive, right? I'm not saying epsilon machines can never be conscious. I'm saying, okay, build me an epsilon machine with certain kind of material, certain kind of physical system that you build an epsilon machine in, and let it do what it's doing. And so once we have the system S defined very concretely, physically, let me then go in and check if it satisfies these conditions. And then the question becomes, okay, what if I build an epsilon machine physically that doesn't satisfy these conditions? Why isn't that system not conscious, right? That's the next part of the question that needs to be answered. Because if I'm going to say it's conscious only if it satisfies these conditions, because you can think of a way to build the epsilon machine, a system that does the same thing that this does, that doesn't necessarily have to satisfy the condition. I mean, that essentially, there are multiple ways in which, because these computational descriptions are descriptions we impose on systems. So you can find a system that essentially can achieve the epsilon machine, but need not satisfy the energy efficiency part. And the question then becomes, if you're going to say that epsilon machine is not conscious, why do you say that? And that comes back to, why do you prefer these thermodynamic conditions over functional conditions? And that always goes back to my own conservative approach, where I'm saying, if all conscious systems that we agree to be at least are conscious are all these recurrent systems, or all these, have a very specific recurrent structure and not pivot structure, then you have to come up with a description that accounts for that. And if functional, it might very well be the case that ultimately consciousness is completely purely functional, right? But unless I see a feed-forward brain, until I see that point, all I can best work with is a description that tries to say, oh, only recurrent structures based out of organic substrates can exist. And that's the best I can do. So, and at this point, in that sense, I think thermodynamic descriptions are a little bit more specific than functional descriptions are.
Yeah, I see. I mean, yeah, I guess my problem is just, I would like to get an intuition for what these thermodynamic conditions you mentioned mean in a system where I don't have heat bath and energy and work, because I don't understand what these things are. So,
I mean, so a great way to think about this is, are you familiar with Hopfield-Boltzmann networks?
Hopfield?
Hopfield-Boltzmann machines that we do in Boltzmann learning.
Yeah, I have a rough idea.
So ultimately, what we're doing is you're saying, okay, any physical system, you say this is my system of interest, right? This is the system that I think is doing some kind of information processing work, and then I'll say, let's say that there is.
Wait, 1 second before you start. I will not. The thing is, what if I don't have a Hamiltonian? That's what I want to know. Like, you don't get energy. Like, you cannot use the word energy. Can you still explain this to me?
You don't have a Hamiltonian for a system.
Yeah, no. I just have basically a Markov chain or a dynamical law, like some function. Dynamical system. Yeah.
I mean, if you in the case of okay, yeah. So that is a problem there, because again, these are descriptive conditions in the sense that if I don't know, so if I'm given a system and I'm told that this is my physical system, and you tell me I need to know whether the system is conscious or not, then at best I can do is evolve the system in time physically, and then try and make experimental measurements if I don't have access to the Hamiltonian. If I cannot.
No. Okay, wait. Okay, again, I guess. But I understand why you I mean, I see how you can understand what I said in exactly this way, but that's not what I mean either.
Oh, okay.
So the thing is, I'm interested in consciousness as a mathematical theory, not as a physical theory. I don't care about physics. So that's why I want to know what it would mean if I basically, as a dynamical systems, so I'm interested whether you can formulate consciousness only as a property of some dynamical systems. And
I mean,
yeah.
Okay, go on.
So there you don't get basically all the terminology from physics for free. Like you have to say like you have to say where you get energy from, like where you get your Hamiltonian from if you don't have one. If I just say x dot is f of x.
Right.
So can you then, yeah.
So I guess I'm saying you cannot, because yes, so you're saying you want consciousness as a mathematical physical property of a system, of a dynamical system.
Of things inside dynamical systems.
Things inside dynamical systems. And I'm saying that under the thermodynamic framework, you can't separate out the physical from the abstract. Like you can't just have an abstract aspect of it. Ultimately, I'm saying that these are physical processes, and you could have you could build a functional or a mathematical theory that's devoid of the physics of it. But I'm saying that ultimately it might be the case that these might come down to physical properties of the system. That the best we can do is we have gained a lot of knowledge from computational descriptions, and I'm not saying that we reject them, we take, but we also cannot ignore these physical properties of systems, things like actual energy flow and entropy measurements and so on. And the best thing to do is to connect the two of them together and find ways in which one maps onto the other. You're right. If I'm just given the Hamiltonian, unless I actually have the physical system and I can, if I'm given a physical system and I'm told what the exact Hamiltonian is, and I'm told that, if this system under some ideal conditions, this is the energy dissipation, or this is what the energy flow would look like, something like in an Ising model or something, then I can possibly think of a way in which, in a very ideal sense, you can come up with a way in which you can determine whether that system is going to be conscious or not. But in most cases, it cannot, it most likely will depend upon the Hamiltonian of the system. It's very hard to work without that if you're dealing with a thermodynamical picture.
Yeah.
I mean, this goes back to like where the interest lies, is right. Like if you want to build if you're looking at a computational picture, and if you're looking at a dynamical, like an abstract picture, then that's where your interest kind of lies. I'm more like a hardware guy. So for me, it's hard to separate out the physics and the material out of the picture. That ultimately, I want it to be described as a physical process.
Yeah, I mean, I mean, it's going to be, to figure this all out, it's going to be too long a discussion, I think.
Right.
But yeah, I see your point.
Okay. So anybody questions? Yeah, but yeah, if not, then this is maybe just a comment, but it seems to me like this energy efficiency part is kind of interesting. I haven't really seen other people arguing based on this non-equilibrium like thermodynamics perspective. So is there any guy like working on this kind of stuff? Seeing energy efficiency and like intelligence or consciousness?
So it's still very early days in non-equilibrium thermodynamics. There's a lot of theoretical work that's coming out. I think so. I haven't seen a lot of people take it all the way to the extreme as I have with respect to consciousness. I think these thermodynamic conditions kind of like explain consciousness, but there are people working at least on the intelligence aspect of it. I think like some of Jeremy England's students are working on it. Suzanne Stowe, who's at the University of Hawaii, has been working on this for a while. You have Jim Crutchfield, who essentially worked on the epsilon machine. A lot of his students are working on now versions of these where they call it thermodynamic computing. I don't think I got to, if no one doesn't mind, let me quickly share this. I can show something.
Right.
Because there's this idea of thermodynamic computing where essentially currently you design your hardware based on computational descriptions. You think about learning as gradient descent, then you're going to build something that has crossbars and matrix multiplication and so on. But if you think of something as intelligence as a thermodynamic process, then that changes how you build these systems. So there are people kind of working on those things. If you look at the idea of thermodynamic computing, there's not a lot of people who use the term itself. The term itself is pretty new. I know Jim Crutchfield's group uses the term, and they work on some very cool ideas. I think they had a recent paper where they showed that a system that maximizes work done by the system essentially behaves like a maximum likelihood agent, an agent that's essentially performing maximum likelihood algorithms. So there are these mappings that exist between how the system physically behaves in terms of its energy and entropy and how it actually, the kind of computation it achieves. So Suzanne Stoll, Jim Crutchfield, I'm currently working on some ideas with Boltzmann machines where you can build more generalized version of Boltzmann machines, and instead of studying them as an equilibrium process where energy goes to zero, you study them as a non-equilibrium process, and you can get some cool things. Right. Oh yeah, Surya Ganguly out of Stanford, his group does some really cool stuff. I saw some work out of Daniel Bassett and Chris Lin. Daniel Bassett at UPenn does some amazing work in this area at the intersection of thermodynamics and intelligence. So yeah, but it's not a really popular field. Right. There's some ideas here and there.
Can you say which Crutchfield paper that was?
Here, let me quickly run to archive. If I see the title, I should be able to see it. Yeah.
Thermodynamic machine learning through maximum work production?
That might be it. That might be one of the recent papers, because I saw that one pop up very recently. Yeah, thermodynamic machine learning through maximum work production. That's one of the things. Where's the other one? If you go further down, he puts out a lot of papers.
Martin, can you put it in the chat, like the link of the paper?
Yeah, I will. This new Google Scholar is really not as cool as the old one. You can't open stuff in a new tab anymore. It's so annoying.
Right. You have to open the actual paper and then open it up on a new tab.
But still, why? Waste of time.
So here's another paper. I don't know if the paper is out yet, but that's the name of the paper. Trajectory class fluctuation theorems. That's an idea there. You know, it's like small rumblings of people slowly trying to like say, because I don't know who's familiar with reservoir computing here, but it's kind of like similar to reservoir computing, but you design the reservoirs in a very particular manner. So it's still very new work, but yeah, he has some Jim Crutchfield, I think, is like the most well-known guy who uses the term thermodynamic computing and works on those.
Right. Okay. Yeah, before we kind of end this YouTube, but we have one questions maybe from the chat in YouTube. Can you see the maybe I'll pick it up.
Yeah.
From the Skull Xbong. So where is the questions? Okay, so he's or she's asking some static model is missing a reference vector, which would be like steady subthreshold activation of associated neuron by input as a comparison of a future input. Maybe it's pretty too long, so I'll put it in the chat. Okay. Can you see this? The second part. Natesh, can you see this, or maybe not? It's muted. You are muted, Natesh.
Oh, sorry. Yeah, there you go. Oops. Let's see. So I think it's the second one. Thermostatic model is missing a reference vector, which would be like a subthreshold activation of associated neurons by inputs as a comparison to future. I'm not quite sure I understand the question. If one of you guys do, please tell me, because it seems like he's making he's saying, you know, something must be present in the system to account for this. And I think for me, this goes down to we don't know what the computational states are. Like right now, we use spiking and we use synaptic weights and so on, but people in the neuroscience community will tell you that there's a whole bunch of stuff that we're not taking into account that we might have to take into account. There's no reason to think that neurons and synapses are it. I mean, I was at a conference like last week where there's a lot of cool ongoing work on glial cells and astrocytes and how they contribute to computation. So I don't necessarily want to say that so-and-so is the computational state. And that is one of the challenges of this approach, because we operate at this low resolution, high level thermodynamic picture. It's hard to figure out what exactly the computational state is. It could be just be neurons. It could be, neurons and neurotransmitters. I'm not willing to rule any of those out yet. So if it's something very specific to a particular neuron needing to fire, then I'm not saying it's wrong. I'm just saying, like, I can't picture that being the only computational state. It could be more. It's probably more. It's definitely not less. You probably need more than neurons and synapses to account for everything that we are able to do as intelligent and conscious systems.
Right. Thank you. So, yeah, maybe we can stop for the YouTube. So before that, let me advertise the next week. Not next week. Next time, Consciousness Club talk. Let me share. So yeah, thank you very much, Natesh. It's very interesting. I think also like a kind of new perspective, shedding light on the consciousness.
I mean, thank you for having me. So yeah, this was great. Thank you.
Yeah. And thank you very much. And so next time we are going to have a talk by Yuko Ishihara from Ritsumeikan University. She's I think, philosopher. She's working on the phenomenology and also like some study about pure experience from Kitaro Nishida and also Heidegger, and some like the topic about phenomenology. I think it's more like a philosophical viewpoint, shedding light on the consciousness. So please check it out and join the discussion again. Okay, thank you very much for joining us today, and we will turn off the YouTube. Okay. Right, so now we ended the